going. I'm going to go up here. I'm going to go to this. I'm going to go up here. Boom, 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 boom. Chem 2. Chem 2 somewhere 21. Test 2. Nope. Oh, I'm in the meeting. Share screen. There just is nobody here yet.
Progress.
Hey, Jordan, how you doing?
Hello, I'm good. How are you?
I'm doing fine. It's from a couple hours ago. What can I do for you? Anything?
Okay, so I was just gonna let you know that I'm going on vacation this weekend and we'll be there all next week, but I'm gonna do everything I can to still be like in class Tuesday and Thursday, but the connection isn't the best. So I know there's nothing you could do about it, but I just wanted you to be aware that that's like my situation.
No, that's Jordan. I think you're a dedicated enough student. I don't really have that much of a worry about it for you.
Okay.
Okay. Just if you can't attend the meetings, then the meetings will be recorded, and if they're recorded, then you can watch them.
Okay.
We are going to be getting into buffers next week. Okay.
Okay.
Right now, kind of what's happening. Acids act almost the same way as bases. So we're going to be using ice diagrams with acids. But
Okay.
there are some nuances with these. The problems are going to get more and more complicated as we get into this. Okay.
Okay.
And next week, we're going to be getting into things like buffers. What a buffer is it's a solution that resists change in pH.
Okay.
And so, for example, if I wanted to make a buffer of what's in front of you on the screen, I would take the conjugate base, which in this case is acetate, and mix it with the acid, which is acetic acid.
Okay.
Now, basically from Le Chatelier, right? Just knowing from Le Chatelier, if I add acetate into a solution of acetic acid, isn't that going to shift it into the left direction, Jordan?
Yeah.
So if it does that, what happens to the H3O? It doesn't increase when I've added the acid. So that's basically why a buffer works. There's one specific equation that you're going to have to know, and that's the Henderson-Hasselbalch. Just make sure you know that. You can actually solve buffer problems using the ice diagram, but it's easier using the Henderson-Hasselbalch.
Okay.
Where are you going?
We're going to the beach for a week, which is nice.
What beach?
Treasure Island in St. Pete.
Okay. All right. Good for you. So you're going to be around the Cesar?
Around where?
The Cesar, with the hotel, the pink hotel that's on the beach. Or you're gonna be
Uh,
further, no, you're gonna be further up.
yeah, it's called like Treasure Island Beach Club or Resort, something like that.
There are a couple good restaurants there. If you're not, if you're interested, just where Treasure Island gets onto the beach highway,
Mm-hmm.
if you there's a little shopping strip that's to your left, and there's an Italian restaurant in there. I don't know what the name of it is off the top of my head, but it's fairly good.
Okay.
And if you take Treasure Island, that same entryway, and you go north, there is a little French restaurant that's also very good.
Okay.
Take it for what it's worth. I don't know if you guys get out to the beach much or not.
We mostly go to the beach like during the week. Like it's like an annual thing we do every year. So this is like our one and only time we go.
Good for you. Everybody needs a
Yeah.
little breakaway, you know?
Yeah.
Other than that, is there anything else I can help you with?
Um, I don't know if maybe you mentioned it in lab and I just wasn't in about the extra credit for lecture.
I haven't mentioned that yet because I
Okay.
haven't done it yet.
Okay. Yeah, no problem.
Jordan, my whole time yesterday was spent doing, I gave a lab lecture at 8 o'clock.
Mm-hmm.
From the time I ended that lab lecture until I had to go to deliver, I was doing my prep for the online lab and the prep for my face-to-face lab today. So I haven't even thought about it. I will, what will happen is I will deliver that. I will deliver it'll be in a practice quiz, but it'll be labeled extra. I don't even know if I have one. If I have one, I'll just upload it right now. I may have one from before. If so, I'll look at it and see what it's involving. But you will get it, and it is worth 15 points.
Okay. Yeah, it's no problem. I was just curious on when it was going to be uploaded.
Unfortunately for you, it will be uploaded tonight, but it will be due probably on Monday at 5.
Okay. Yeah, that's no problem.
Okay. Araceli, how are you doing?
I'm good. How are you, Professor?
Peachy Keen, wonderful. Just happy to be here. Okay, yeah. I may change question 2. I may change question 2 because you guys got that for the most part. When I did this before, yeah, I may change this a little bit. Talking about the extra credit, Araceli. Okay. I will make it, but it may take as long as this evening for me to post it. It'll be due at 5 on Monday.
Yeah, that's no problem.
Is it like a
Araceli?
quiz? Is it like a test or a
No,
quiz
it's
for
extra credit.
Okay.
Basically, you're going to get to do these. It'll probably be 2 questions. You'll get to do these 2 questions, and those points will be added to your test score.
Okay.
Araceli, do you have any questions?
No. Is the lecture for Tuesday? It's already posted on
Yes, it is.
Canvas. Okay.
I posted it yesterday sometime. I think I posted it yesterday afternoon. Thank you. Can you visualize yourself, Araceli?
Yes. Just 1 second.
And I think Jordan has gone away. No, yep, Jordan's gone away for the moment. Okay, I am. Hey there. Okay. What'd you ask again, Araceli?
Oh, I was just asking about if like the lecture for Tuesday was still on.
Ah, yeah.
Okay,
You're
miss.
asking about whether it was posted.
Yeah.
Hi, Jana. Okay, all the way down here. You know that you can look at these meetings. These were last summer's. I went through the same material. It's just that it won't be the same meeting. But if you need be, you click on that and the links will be located. And as you can see, the June 15th is up there. All right, just click on the
Okay,
link and that
thank
should
you.
load the video. Jana, do you have anything for me? Maybe Jana's no longer here. Jana? Did you go away, Jana? Hi, Ethan. How you doing?
Hello, I'm doing well.
All right, visualize yourself. There you go. Hey, come on. I've got to look at that reef in the back, or else I don't know you're here. Is that a reef or is it a forest? Your background.
It's like a forest,
Okay, like a rainforest.
something like that, I guess.
I can't see very much. Do you have any questions, Ethan?
Not at the moment. Let me see. Like, just gonna-
Jana, you out there, Jana? Okay, Jana doesn't want to talk. Okay, Ethan, while you're doing that, I'm going to just play my wonder word. Okay? Just tell me when you need me, all right?
Okay. Oh, okay. I guess the question I got wrong is just something about the upcoming, like,
Okay, which one are we
Stuff.
talking? The quiz?
yeah. Yeah, it's just like when you're considering polyprotic acid, you can generally ignore the contribution of the second proton to the overall H3 plus concentration, and I answered false for that.
Generally speaking, Ethan, what happens, and we're probably going to get into it today, the equilibrium constant for the second proton is so much lower than the first one, okay, that there's not much production to begin with out of that.
Oh, okay.
And second thing, if you consider, okay, if you consider, I'm going to go to the very bottom of here so I can add something. Sir, home. Thank you. Home. Home. Okay. All right. Say if I have something like H3PO4
Hmm.
and that's in, yeah, actually, the first one is fairly strong. Damn it. So I mix this with water. And I make H2PO4. But now this is a minus charge because I've taken one of the protons away, plus
Mhm.
H3O. That makes sense,
Yes.
Ethan? Now, if I'm going to get the second one, if I'm going to grab the second one out of there, this is All right. Okay. Say this Ka is equal to something reasonable like 2. I'm not saying this is true, but it's like this. Actually, I could look it up. Maybe I can look it up. You know that your books have appendices in the back.
I do.
Yes. Look at the very back. And you're going to need these. Okay. It's at the very back of the book. It's especially appendice 1 and 2. Or yeah, appendice B. That gives you thermodynamic quantities that we're going to need next chapter. And C gives you equilibrium constants. Okay. Now I'm looking for, okay, phosphoric. Okay, 7.5 E to the minus 3. All right, just looking at hydrogen phosphate, dihydrogen phosphate. Ah, crap, it's not in here. Say, for example, what would happen is this Ka would be something on the order of, say, 1.2 E to the minus 7th. Okay?
Okay.
Now, just looking at these two Kas, this one is an order of magnitude 4 times what the bottom one is, right?
Yep.
All right, second point. Isn't the first one producing H3O plus?
Yes.
A whole bunch of H3O plus in comparison with the bottom one. So if you have H3O plus, isn't that going to shift the equilibrium of the bottom one to the left? So there are 2 factors that go on here. First of all, it's harder to pull a proton off of a phosphate after it's a negative charge already. Does that make sense, Ethan?
That does, yeah.
All right, so it's harder to do that to begin with. And the second factor you have working against you is by Le Chatelier, the H3PO4 is putting H3O plus into the solution, which for the second reaction is pushing it further back to the left. So do you produce a couple H3O pluses from the second reaction? Yeah, but it's really not significant with the amount of H3O plus that is produced from the first. So each subsequent hydrogen, even the next one down. Now you understand why I have a hard time doing these things. So if I go HPO4, 2 minus, plus water, to PO4, plus H3O. This Ka is going to be even smaller. Again, do not quote the first one's legitimate, the next 2 are not. The next one's going to be even smaller. So literally speaking, I don't have to worry about the second reaction producing H3O plus and the third one, because the Kas are so low, it produces insignificant amounts of H3O in comparison with the first one. So I can literally just ignore those. If the amount they produce is not significant. Got
Okay.
that, Ethan?
Yep.
And that's basically how we're going to solve those particular problems. Anybody else have any other questions, guys? Ether?
I do have a question, but it's in the quiz.
Okay.
It was, I guess it was the first question because I,
Let me get back out of here. I'm going to stop share for a second because I'm in the slideshow. Okay, and I'm going to share screen again. Okay, which quiz was it, Ether? Do you remember the number?
8. Quiz 8.
Okay. All right. I'm going to go edit. Yes, it's going to give me a bad message. All right, which question was it?
It's question 1.
Okay. All right. The conjugate acid, when I say conjugate, and I'm going to go, this is the first thing I'm going to go through when we resume. Conjugate acid is going to be on the product side. So it's going to be either this or this. Okay.
So I chose HCOO negative, but it was wrong.
Yes. First of all, H3O is a strong acid. If you just have H3O, it's going to lose its proton fairly readily. Now, I have to go and go back to the slideshow. The actual structure of formic acid is this. Okay, I've already made a mistake. Okay, and what you have to understand is this is an organic acid. Okay. Now, organic acids have covalent bonds of H with something and ionic. In this particular case, whenever you see a carbon linked with a hydrogen, that is a covalent bond. All right. So this hydrogen cannot be taken away from the carbon. So when I make this plus H2O, I'm going to make a equilibrium that makes that H is still hooked onto the carbon, which is still double bonded to another carbon, but I now have that hydrogen being taken away because I have that hydrogen bonded to the oxygen is an ionic bond. I can take that hydrogen away. I can't take covalently bonded hydrogens away. So this has only one hydrogen to lose. And so we also have H3O plus. So given the choice between formic acid and H3O plus, this is the conjugate acid. I am going to change that question in the future. I am going to make that to be what's the conjugate base. Okay, because that fact that you have to realize that this bond here is covalent, and so you can't lose that H. Fair enough,
Yes.
Ethar?
Yes. Just also a question 9.
Question 9.
Yes, please.
Okay. This is something that you should have gotten from the reading of the chapter, or the reading of the chapter, or the PowerPoints. What happens when you put salts into water? We're going to go over this today. I'm trying to find. All right. I'm going to share screen and go back here. All right. You would think that you put a salt in water that it's just going to be neutral. Wouldn't you think that, Ether?
I chose the second option.
Which was?
It's less than 7, less 7. The
Okay, it's
pH.
actually going to be greater than 7, and I'm going to explain right now why. Not insert, I need a new slide. Okay, I have sodium acetate. So that means I have a sodium ion plus CH3, H3C. All those hydrogens are bonded to the carbon covalently. Then I have another carbon, just like I did before with the formic acid, only this time I have acetate. Okay? Plus water. Now, what happens with this? Na plus water no reaction. I get no reaction when I put Na plus is not strong enough to pull the OH off of water. It's not strong enough. On the other hand, my acetate okay, let's do this over here. Boom, 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 boom. Make this a little more understandable. Do you see ether where we have an oxygen there with a minus sign on it? Do you see that, ether?
Yes.
Okay, this is strong enough to pull an H off of hydrogen or off of water to make this entity. Athar, does that make sense to you?
Yes, sir.
So this is strong enough to pull a hydrogen off of H2O. If it pulls a hydrogen off of H2O, what's left? Pulls an H plus off of H2O, what is left? You take an H away from H2O. Okay, Ether, H2O has how many hydrogens? Okay, you take one away. How many hydrogens does it have? Does
Just
it still
one.
have the oxygen, Ether?
Yes.
So we have OH, right? We took away H plus. This left an extra electron over there. So we have an OH minus. Now, what is happening here? Are we generating OH minus?
Yes.
We're generating OH minus. OH is a base. So when we put sodium acetate into solution, the sodium doesn't react with the water. There's no reaction, but the acetate does react with water to protonate the negative oxygen, making acetic acid again. Plus, it generates OH minus, which is a strong base. So that's why when you put sodium acetate in the water, you make a pH that is higher than it was before. Does that make sense, Ether? We're
Yes.
going to go through that. We're going to go through that in detail today.
Thank you.
Okay. All right, ladies and gentlemen, any other questions? I announced it earlier. I did announce it earlier, but I want to make sure that you all understand it. I promised you an extra credit question. I have not delivered that yet. I will, a question or questions. I will deliver the extra credit question. It will be in the form of a practice test. I will deliver that sometime after I get home tonight from my face-to-face lab. That question, those questions will be due by Monday at 5. You can add up to 15 points to your test score. Any questions? It will be something that I have covered. Only be aware that it's probably something that is probably a question that you didn't do very well on the test. Or maybe something new that I covered. Any questions, ladies and gentlemen? Okay. Nothing? We're good, guys? Talk to me.
Yes, we're good.
Good.
Okay. Now, I believe I left off with conjugate acids and bases. Did I not? Ethan, is that where I left off?
Yes.
Let me check. Yeah, it's just to
Somebody
kind of-
said yes. Who was the yes person?
Natalia.
Thank you,
That's where I
Natalia.
ended my notes.
Okay. Now, what happens when you put an acid into a situation? Immediately, what you're going to make is that acid is going to make a base out of something else. When I put it in the water, the acid is going to donate its proton. If I have nitrous acid, that the H from the HNO2 is going to donate that proton to the base. Base is the acceptor of the proton. So I have two new entities, NO2 minus and H3O plus. Okay, now the NO2 minus, it's missing a hydrogen. So it can accept that hydrogen back to regenerate nitrous acid. So in effect, the product one of the products can accept the hydrogen back and regenerate the reactant. The other one, the conjugate acid, can donate that hydrogen to the other one. So when it donates the hydrogen, it becomes the conjugate acid. Easy way to figure this out. Look at the acid. The acid is going to donate a proton. Its pairing is going to be the conjugate base, and the conjugate base is going to be the same compound as the acid. It's just going to be missing an H. And it can act as a base and grab a hydrogen from something else. If you look at the base is going to be the same as the conjugate acid, only it's going to have an extra proton, and it is going to be a plus. Now, I'm going to shift all the way down to the bottom here. Something I need to explain. This is acetic acid. This is the way acetic acid is drawn organically. I have 3 hydrogens bonded to the carbon, which is bonded to another carbon. That second carbon has a double bond oxygen and a single bond with an oxygen that has a bond with the hydrogen. Do we understand how this is structurally? Do we understand that?
Yes.
If you don't understand, talk to me. Now, the 3 hydrogens that are bonded to the carbon are bonded covalently. That bonds can't be broken. So these are non-titratable hydrogens. These do not split off and make a bond. In other words, if I'm looking at an acetate here, these 3 hydrogens bonded to the carbon are bonded covalently. They don't act as acids. They stick with carbon the whole time. It is only the one that is linked to the oxygen, the single bonded oxygen. That is the only one that is titratable. Unless, of course, I have 2 of these type of groups, C double bond O dash OH. If I have 2 of those on my molecule, then that is also, the second one would be a titratable. It's only the hydrogens bonded to oxygen that are protons that can act as acids. Do we understand that, ladies and gentlemen? So the conjugate base is in the products. It's going to be the product, and literally speaking, it's the product that can accept a proton from an acid. The conjugate acid is also in the products, and what it can do is it can donate a proton to a base. So I have acetic acid plus water making an acetate minus plus H3O. What on the product side can accept a proton? C2H3O2 minus or H3O plus? Which one of those 2 can accept a proton?
The C2H3O2.
So that if it accepts a proton, that's the definition of a base. It's on the product side. That makes the acetate, the C2H3O2, that makes that one the conjugate base. It gets paired with the acid. The acetate gets paired with the acetic acid. A way to determine this is just look at the products. The conjugate base will have all of the elements of the acid except one proton. On the other hand, the conjugate acid is the one that can donate a proton. H3O can certainly donate a proton and go back to H2O. Since the H3O is on the product side and it can donate a proton, it is the conjugate acid. It can be linked with the original base, the original thing that accepted the hydrogen to begin with. Do we understand that, ladies and gentlemen? Okay, Parker. In these, I've got OH minus reacting with HCO3 to make CO3 2 minus in water. Parker, look at the left first. Which gave you a hint there. Which one of those reactants can donate a proton?
The HCO3.
So I've got the HCO3 is donating it. Which one is accepting it, Parker?
The OH.
So I've got my base and I've got my acid. Now, Parker, look on the right side. Is there a product on the right side that looks like the acid minus the hydrogen?
Yeah, the CO3.
So the CO3 can accept protons to become HCO3. So it is the conjugate base. The H2O can donate one of its protons to the CO3 2 minus to make it an acid. Linking, again, linking the two pairs, I have the OH grabbing a hydrogen and the H2O donating it. So those two are linked as the original base in conjugate acid. My CO3 2 minus is the conjugate base. It can accept protons. My acid delivers them. Guys, do you have any questions about conjugate acids and conjugate bases? Good. Since you have no questions, then you can answer my questions. Let's see. I got 22 of you in here. Emily,
Yes.
look at the two compounds, HF and SO3 2 minus. Which one can donate a proton?
The HF,
Which one can accept the proton?
the SO3.
So donating the proton, the HF is my acid, accepting it, my SO3 2 minus is the base. So of my acid, do you see something on the right that looks like my acid minus an H plus?
The F.
My F minus. So my F minus is my conjugate base. Do you see something on the right that looks like SO3 with an H attached to it?
HSO3.
So that's going to be my conjugate base. So you have to understand my conjugate base, which is the F minus, can accept a hydrogen from the conjugate acid to regenerate the reactants. Does that make sense, guys? CO3 2 minus and acetic acid, making acetate and HCO3. Benita,
Yes.
okay. Again, between CO3 2 minus and HC2, H3O2, Do I have something that can donate a proton?
The acid. I don't know. I'm guessing at this point.
Well, I'm trying to get you to identify the acid. Which one is the acid?
Oh, the HC2 H3O2.
That is my acid. So what can accept a proton?
Is it the base?
Which thing? Tell me which one. Which specific thing? CO3 2 minus or
negative. Yeah, the minus.
CO3 2 minus can accept the proton. So I got to look over at my product side. Benita, which one of these two can donate a proton?
HCO3.
So that is going to be my conjugate acid. What is my conjugate base?
The C2H3O2 minus.
Exactly. My HCO3 minus is linked with my CO3 2 minus. Conjugate acid is linked with my base. My acid is linked with my conjugate base. Benita, is this making a little more sense to you?
A little bit, but I just need to practice this more.
You want to practice on the next problem?
No, somebody else can do it.
I kind of figured you'd say that. Okay, Jennifer.
Yes.
Okay. Look at these two entities, the two reactants. Which one's going to donate the proton and which one's going to accept it?
The H3PO4 would be the acid. The OCO would be the base.
All right,
The
we're going to.
OCO accepts the hydrogen, while the H3PO4 donates one.
Okay. Now, this is going to be a hard question, Jennifer, because you have two possibilities here. When I ask you, you have two possibilities of donating an H, don't you, Jennifer?
I
Either
suppose-
one of these could deliver an H, right?
Mhm.
HOCl. All right, a couple points. Is it going to be harder to take a hydrogen away from a negative ion? It's already negatively charged. If I try and pull a positive hydrogen from a negatively charged ion, is that going to be harder than taking a hydrogen from a neutral acid?
I suppose it would be harder from a
It's going
negative.
to be harder for the H2PO4 to donate another hydrogen to the HOCl. Does that make sense, Jennifer?
Yeah.
So which one is actually going to be donating the proton?
Would it be the HOCl to the negative?
Because if this accepts an H, I get rid of that positive charge, right? So if HOCl is donating the hydrogen, does that make the HOCl the conjugate acid or the conjugate base?
Would it be the conjugate acid?
It's the acid because it's donating the proton. Jennifer, what is accepting the proton?
That one that you're pointing to, the H2PO4?
It's accepting it. So it is, because it's accepting it,
Conjugate
it
base.
is the conjugate base. Are we good, guys? Are we good? All right. Strong acids. And we're basically talking, I'll give you a list of those later on, but strong acids completely dissociate in water. In other words, if I have HCl and I add water to that, it is not in equilibrium. HCl plus water goes completely to make H3O plus and Cl minus. H2SO4 plus water goes completely to make HSO4 minus plus H3O, 100%. What that means when I say it makes it 100%, the conjugate base of a strong acid is so weak, it cannot grab a hydrogen off of a hydronium ion. So the reaction goes in the forward direction. It does not go in the reverse. On the other hand, if I have a weak acid like acetic acid, like hydrogen carbonate, like carbonic acid, HF, they only partially dissociate in water. In other words, if I have HF, I don't get 100% of the HF being converted to F minus and H3O plus. I get a little bit of the HF going to F minus and H3O plus. What this means is that the F minus can readily grab that H3O, the H off of H3O to remake the HF. So F minus, if I have a weak acid, the conjugate base is relatively strong. Strong acids, weak conjugate base. Strong base, weak conjugate acid. Weak base, strong conjugate base. Strong conjugate acid. Do we have this concept down? So basically, if I have HA in water, what happens when I first put it in? They're together. As I'm adding the water, as time, if I have a strong acid, I get complete dissociation. The anion is completely separated from the proton. Would you think this is going to be conductive? Would this solution conduct electricity? Yes or no answer. Who wants to take a 50-50 shot? Jana?
Yes.
I'm completely dissociating it. I've got lots of ions in solution. Remember, in order for a solution to be conductive, it has to be an electrolyte, which is complete dissociation. So strong acids very much conduct lots of electricity. On the other hand, if I have a weak acid, what happens is only part of the molecules dissociate. Would this be conductive? Jessica? Jessica?
Yeah.
Would it conduct electricity, the weak acid? Do I have some ions in solution?
Yes.
I have some ions in solution, so it will conduct electricity. Is it going to be a strong current? Do I have a lot of my molecules dissociated into an anion and H plus, Jessica? Look at the ones that are flashing.
It'll be strong.
All right, the ones that are flashing are the ones that are dissociated. Those are the ones that are creating ions. What's the relationship between the ones that are flashing and the rest of them that aren't flashing? Do I have a lot that are flashing?
Just less.
So I have very, very few that are dissociated.
Mhm.
It will conduct electricity, but the current is going to be very, very weak.
Oh,
And what's happening here is I'm getting an equilibrium. The ones that are flashing, eventually they will grab a proton, and when they grab a proton, one of the others will lose, one of the ones that is together will lose its proton. Remember, it's an equilibrium. The H pluses are reacting with the A minuses to make the HA at the same rate that the HAs are reacting to make H plus and A minus. In any acid-base reaction, the equilibrium will favor the reaction that moves the proton to the stronger base. So if I have HCl in water, remember I said that was a strong acid. Moving the H to the H2O. H2O is a much stronger base than Cl minus. It's so much better a base that the K is much, much greater than 1. There is a negligible amount of the reaction going back to reform the H2O and the HCl. On the other hand, if I have acetic acid in water, the acetate is a much stronger base than the water is. Because the acetate is a much stronger base, it favors remaking water and remaking the acetic acid. In this case, my equilibrium constant is much less than 1. So because a weak acid or base is not complete, we have an equilibrium that gets established. And if we have an equilibrium that's established, we can create a constant. Because it's a special case of either creating an acid or a base, we call that constant Ka or Kb. If I have a generalized acid dissociation, because we do not put water into an equilibrium constant equation, my equilibrium constant would be A minus concentration times H3O concentration divided by my HA concentration. Because it's an acid, it gets designated a special K. It is K sub A. Just like equilibriums, the constant can be expressed as a product of the concentration. Again, remember, H2O is never included in a Ka expression. Now, let's go previously. Okay. Remember, we're judging our strength of our acid on the amount of H3O plus. So if Ka is big, what does that say about the relative concentration of H3O in relationship to the original acid? Jenna?
I don't know.
Okay.
Yeah.
Ka is big.
Okay.
If I want a big Ka, am I going to have a big numerator or a big denominator?
Oh, big numerator.
So look, how do I get a big numerator? Do I have lots of H3O or do I have lots of HC2, H3O2?
Lots of H3O.
So again, if my concentration of H3O is high, I have a high Ka And if the concentration of H3O is high, that means I have a stronger acid. Ka can be equated to the strength of the acid. The bigger the Ka, the more H3O I have, and the stronger the acid. So if I am going to compare let's go with, let's see who else is in here. Oh, yeah, I can do that. Natalie. You there, Natalie?
Yeah, I'm here.
If I have phenol versus nitrous acid, from what I just said, phenol's Ka is 1.3 times 10 to the minus 10th. Nitrous acid is 4.5 times 10 to the minus 4th. Which Ka is bigger?
The -4.
4.5 times 10 to the minus 4th. The nitrous acid has a bigger Ka. Which one is the stronger acid?
The Phenol.
Remember what I said a few minutes ago. Which one did I say was stronger? Bigger Kas or smaller Kas?
Bigger Ks.
So which one is stronger? Nitrous or phenol?
Nitrous.
Nitrous acid is stronger than phenol. Okay. If I am looking at factors affecting acid strength, if I'm looking at a monoatomic acid, a binary acid. In other words, I've got H just hooked with another element. As I go down the periodic table, do my electronegativities get bigger or do they get smaller? Guys, if you haven't figured it out by now, if I don't get an answer, then I go and ask the question of everybody or ask a specific person. Can anybody tell me whether electronegativities get bigger as you go down a column in a periodic table?
It increases.
Does the electronegativity increase as you go down the periodic table?
No, doesn't it go increase as you go up it?
It goes up because you are closer to the nucleus with fluorine than you are with bromine. Okay? So fluorine has a stronger electronegativity. So if it has a stronger electronegativity, is it going to want to hold on to a positive proton more or less than HBr is?
More.
The HF will want to hold on to the hydrogen more. That means that HF doesn't dissociate as well as HBr does. That means that HBr is the stronger acid. Did you follow my logic? Anybody need me to explain that again?
Can you repeat that again, please?
Okay. Fluorine has a stronger electronegativity than bromine does. So fluorine wants to hold on to its positive hydrogen more than bromine does. What that means is that hydrobromic acid will dissociate more than hydrofluoric acid. If it dissociates more, I've got more hydrogens in solution. If I have more hydrogen solutions, the acid is going to be stronger. Are we getting that?
Can you rephrase that as like being the stronger the electronegativity, the stronger the acid is?
Wrong.
No?
Stronger the electronegativity, the weaker the acid.
Oh, okay.
because because the stronger the electronegativity is, it wants to hold on to that proton. So if it wants to hold on to that proton, then it's not going to dissociate. The H is going to be linked to the F. It's not going to go out in solution as much as the HBr. Weaker the electronegativity, the stronger the acid. Weaker the electronegativity, stronger the acid. Okay. If I have an oxyacid, this is something like SO4. This is something like HClO. This is an acid in which the hydrogen is attached to the oxygen, and that oxygen is attached to another element. Now, the more electronegative the element, this is going to be exactly opposite what we just said. The more electronegative the element is that's attached to oxygen, the stronger the acid. Let me repeat that. If H is just attached to the element in the terms of a binary acid like HBr, H2s, something like that. If I just have a binary acid, the more the electronegativity, the weaker the acid, because the H is directly bonded to that element. On the other hand, if I have an oxyacid, the hydrogen is attached to the oxygen, and that oxygen is attached to another element. When I have an oxyacid, the exact opposite is true. If I have an oxyacid, the more electronegative the element that's attached to oxygen, the stronger the acid is. And it can be explained. When I have chlorine, a very electronegative element, what it's doing is it's pulling a little bit of this negative charge that's on the oxygen to kind of stabilize the molecule. Iodine can't do as good a job at stabilizing because it's not as electronegative. Come back at me, guys. You are going to have to do this on the test. I'm going to give you an example of 3 or 4 acids, and you're going to have to tell me which is the strongest and which is the weakest. Does anybody not understand this?
Okay, so the stronger, like in the previous slide, is like a stronger electronegativity means like a weaker.
No,
Yes.
no. Exact opposite, Ethan. If I have a binary acid, this means the hydrogen is directly attached to the element I'm looking at for its electronegativity. Okay, Ethan?
Mhm.
Like H is attached directly to the F, H is attached directly to the Cl. Okay? So this means that with F, I have a real strong attraction because it has a very high electronegativity.
Right.
So that F is really attached to the hydrogen. So it makes, because it's really attached to the fluorine, that means that it stays as HF and doesn't dissociate as H plus and F minus. On the other hand, bromine, less electronegativity. This means that the bromine is not holding on to the hydrogen as strongly. The hydrogen can then dissociate into water as H plus and Br minus. Are you good with that, Ethan?
Yeah.
Now, when I'm dealing with an oxyacid though, I have to realize that if I have a real electronegative atom that's attached to my oxygen, it is pulling some of the electronegativity away from the oxygen. Because it's pulling some of that electronegativity away from the oxygen, that makes the oxygen have less of a negative charge. If it has less of a
Okay.
negative charge, it can release its hydrogen more easily. Did that come through, Ethan?
Yes.
Iodine doesn't have as strong an electronegativity. So it's not going to make the oxygen negative charge as weak as the chlorine does. So because of that, because the iodine is weaker than chlorine is, this negative charge is stronger because it's linked to iodine. Because the negative charge is stronger, it wants to link to the hydrogen more, which makes it a weaker acid than HOCl.
Okay. Okay, I get it now.
All right, Ethan?
Yep.
If I put more oxygens on an atom linked to the hydrogen, understand the hydrogen that gets released is the one that's linked to the oxygen. If I put more electronegative ions, if I have one attached to the chlorine, which is attached to the oxygen, attached to the hydrogen, if I only have one as opposed to two, which one is pulling more negative charge away from the oxygen? The one with one oxygen or the one with two?
The one of two.
If it's pulling more negative charge away from the oxygen, that means the attachment for the oxygen attached to the oxygen is weaker. Because that attachment is weaker, the hydrogen can dissociate in water better, so it's a stronger acid. If I put 3 around it, that's even a more stronger acid. More stronger? You can tell I'm an English major, right? If I put more oxygens around it, it's an even stronger acid. All right, bottom line. If you don't want to think logically like that, if you just want to memorize it, write this down. If the hydrogen is directly attached to the element, then the stronger acid is the element with less electronegativity. As you go down the chart, they have less electronegativity. So as you go down the periodic table, you increase the acid strength. If there is an oxygen between your element and the hydrogen, the element that is more electronegative makes a stronger acid. It's exactly opposite from the binary acids. Binary acids, weaker the electronegativity, the stronger the acid. Oxyacids, the stronger the electronegativity, the stronger the acid. The more oxygens I have attached to the element that's linked to the oxygen with the hydrogen, the more oxygens I have around that element, the stronger my acid is going to be. Between Ph3 and H2s, Leonardo, which one? Identify, these are both binary acids. Identify which element, either the P or the S, identify which one is more electronegative, and then tell me which is the stronger acid. Leonardo.
S is more electronegative.
Okay, so which is the stronger acid? PH3 or H2S?
pH3.
pH3. The hydrogen is directly attached to the element. Phosphorus, less electronegative than sulfur. It's going to have the stronger acid quality. Okay? Parker. HNO2, HNO3.
It's gonna be the one with the more oxygens.
We're going to
It's gonna be the stronger acid.
We're talking about nitric acid. HNO3 is stronger than nitrous acid, HNO2.
Yes.
Okay, Jordan. Tricky question, Jordan. I have this compound has an H linked to an O, linked to an S with 2 oxygens around it. This one has an H linked to an O, linked to an Se with 2 oxygens around it. What is more electronegative, S or Se?
Is it Se?
Which one is higher on the periodic table?
Oh, S.
So S is higher in the periodic table. It is the more electronegative. Now, going back to this slide. Remember, the S is linked to the O, which is linked to the H, or I have an Se linked to the O, linked to the H. Which one is stronger? The one that has the S linked to the O, or the one that has the Se linked to the O?
The S linked to the O?
Because it's pulling more of the negative charge away from the oxygen. If it does that, it makes the link between the hydrogen and the oxygen weaker. If the link is weaker, there's more H dissociated, stronger acid. So yes, you are correct.
Professor, I have a question.
Yeah, Jenna.
So would you ever ask us to compare like a binary acid with an oxyacid, or like judge which one's stronger?
No.
Okay.
No.
Perfect.
No, I will not do that. I could, but I won't. Like, for example, I'm telling you right now, this is something you're going to have to memorize. I have no mnemonic for this. The 7 acids that completely dissociate in water, 100%. If I have 1 molar HCl, I have 1 molar H3O and 1 molar Cl minus. If I have 1 molar perchloric acid, I have 1 molar H3O and 1 molar perchlorate. These dissociate 100%. The lists are here. Hydrochloric acid, hydrobromic acid, hydroiodic acid. Every binary acid except HF is a strong acid. Plus I get nitric, sulfuric, and chloric acid and perchloric acid. I'm sorry, I had to think what the anions were. Chloric acid, HClO3, and perchloric acid, HClO4. Those are the 7 strong acids. Bases. Again, for these acids, for the monoprotic, in other words, H2SO4 going to HSO4 plus H3O. The monoprotic, the first hydrogen coming off of sulfuric acid, the H3O is going to be equal to the concentration of my acid. Now, the strong bases are alkali metal hydroxides and the heavier alkaline earths, calcium, strontium, and barium. Those, all the alkali, all the ones in the first column, if you link those with OH, those are all going to be strong bases. When I'm dealing with alkaline earth metals, It's just calcium, strontium, and barium. Again, they all dissociate completely in aqueous solution.
Oh, wait, Professor. So for the alkali metals, you said it was all of them, but
Yes,
for the alkali earth metals, it's only those three.
correct.
Okay, thank you.
What it has to do with the fact is that the bigger the alkaline earth, you get the OH that's further away from the nucleus of the Ca. So if it's further away from the nucleus, it's not attracted as much. Does that kind of make sense, Steve?
Yes, it does.
Anything else, guys? Okay. Pure water. Can you swim in pure water in an electric storm?
No.
Pure water. Actually, you can. If I've got water reacting with water in a reaction called an auto-ionization, I do make H3O and I do make OH minus, but I make very, very little of it. I make very, very little H3O plus and very, very little OH minus. So if I have pure water, I could actually swim in an electric storm. Trouble is, you can't get pure water. Just the fact of water being around our atmosphere with the carbon dioxide reacts with water to make carbonic acid, which makes ions. It's the ions that transmit the electricity from the lightning that caused the problem. If I have just water, this reaction occurs very, very slightly. So again, I can't count water in my equilibrium constant. All I can count are the ions. So my equilibrium constant for this reaction is just the concentration of my hydronium ions times the concentration of my OH ions. This is a special equilibrium constant that's referred to as Kw. At 25 degrees, normal room temperature, Kw equals 1 times 10 to the minus 14th. So if Kw equals 1 times 10 to the minus 14th, what's the concentration of my H3O? Math question. Oh dear God, he's asking me math. H3O concentration equals OH minus. So this becomes X squared is equal to 1 times 10 to the minus 14th. What's the value of X? Ethan? Do a calculator. Somebody at least do it on a calculator. Take the square root of 1 times 10 to the minus 14th.
Yep, okay. One, or, wait, 1, 2. So it basically just turns into 1 times 10 to the power of negative 7.
If I take 1 times 10 to the minus 7th and multiply it by its equal concentration, 1 times 10 to the minus 7th, I get the equilibrium constant of 1 times 10 to the minus 14th. So I get my concentration of my hydronium ion. Remember, H3O plus equals OH minus at neutrality. My water is neutral. They equal each other. At that point, my H3O plus is equal to 1 times 10 to the minus 7. pH is defined as negative log of my H3O concentration. In pure water, my H3O equals my OH minus. My H3O concentration is 1 times 10 to the minus 7. The log of 10 to the minus 7 is negative 7. Negative a negative 7 is 7. This is why the neutrality, the pH at neutrality is 7. Now, if my acid has a higher H3O concentration than pure water. So if it has a higher H3O concentration, that means this exponent number is going to be smaller. If the exponent is smaller, then the log of this number is going to be less in magnitude. So my pH is going to be less than 7. A base has a lower H3O plus concentration than pure water. What that means is that this exponent is increased. Again, the log of a number that is raised to a higher power of 10 is going to be a bigger number than 7. So the pH is greater than 7. (3.32). Natalie, is that an acid or is it a base?
An acid.
Very good. Valeria, 12.22. Is that an acid or a base?
I would say it's an acid.
Let's go back to the previous slide. 12.22. Valeria,
Yes.
is that going to be an acid or a base?
A base.
It's higher than 7. It's going to be a base. Cherie, how about 7? Is that an acid or a base?
Would it just be neutral?
Trick question. You got it right. Good. If you're interested in it, this is a slide. If you notice, rain has a acidic content. That's because there's carbon dioxide in the air. Okay. If you have something like Coca-Cola, that has a pH of 3. You have something like bleach that has a pH of 12. So bleach is a base. Coca-Cola is an acid. There are other P scales. The P in the pH tells you to take the negative log of the H plus concentration. If I have a POH, this means it's negative the log of the OH concentration. A pKa, remember the Ka is your equilibrium constant. A pKa is negative the log of the Ka. Okay. So if my H3O concentration times my OH minus concentration is equal to Kw, that means that it's equal to 10 to the 1 times 10 to the minus 14th. If I take the negative log of my H3O plus my negative log of my OH, which is my negative log of Kw, they're all equal to 14. This is my pH. This is my POH. Add pH and POH, I get 14. Copy that down. You will need that. pH plus POH equals 14. So let's talk about pHs and strategy. If you're given the pH and you want to know the concentration, in your mind, make that number negative. You're going to hit the 10 to the X button on your calculator, plug in the negative pH, hit enter. The answer will be the concentration. If you have the pH and you want to know the concentration, hit the 10 to the X button on your calculator, type in the negative pH, enter. The answer you get will be the concentration. It will be a low number. On the other hand, if you have the concentration and you want the pH, hit the log key. Type in your concentration. Hit enter. Then after you hit enter, you are going to get a negative number. Just make it positive. So if you're given the concentration and you want the pH, hit the log key, plug in the concentration, multiply that number by -1, and you will get the pH. Guys, what if we take a break for 5 minutes? 5-minute break, I'll be back. Okay, I'm back. I am back, ladies and gentlemen. Jordan, are you here?
Yes.
Ethar? Ethar?
Yes.
Thank you.
Yes, I'm here.
Vanessa? Vanessa? Natalie?
I'm here.
Thank you, Vanessa. Natalia?
Here.
I'm here.
Lisa?
If you said Natalie.
Okay, Natalie, I'll catch it on the way. I got you. Benita? Benita?
Here.
Sarah? Sarah? Gianna? Jenna?
Here, sorry.
Jennifer?
I'm here.
Manuel?
Here.
Parker?
I'm here.
Cherie?
Here.
Araceli?
Here.
Jessica?
Here.
Keanu? Valeria?
Here.
Jana?
Here.
Leonardo?
Here.
Anaya?
Here.
Natalie, I just called you. Satori?
Here.
Raylena? Raylena? Rhea?
Here.
Emily?
Here.
Delexis? Ethan?
Here.
Thank you. Thank you, ladies and gentlemen. Of the people that I possibly, Sarah, Gianna, and Keanu. If you are here, make sure that you tell me. You're marked absent right now. All right, simple questions, guys. Remember, if you have the pH and you want the concentration, hit the 10 to the X button, make the pH negative, type it in, hit enter. That will give you the concentration. If you have the concentration and you want the pH, then type log, type in the number, hit enter, and whatever number comes on the screen makes it positive. Okay, so we have Valeria. I bothered you already, haven't I, Valeria? Sachari,
Yes.
you have a pH of 5.43. What is your H plus concentration?
I honestly don't know.
5.43, write it down.
Can I answer?
No,
Oh, okay.
you
Okay.
have the pH and you want to know the concentration. The instructions are on there. 5.43, what is the concentration? Anaya, give me the answer.
Okay. Okay, hold on. Can you go back to the page?
5.43. That's the pH. I want to know the concentration.
Okay. Is it, oh, hold on. It needs to be negative.
No, it doesn't. It doesn't tell you that. Oh, you said, I'm sorry, never mind.
It needs to be negative, right?
Yes, the exponent needs to be negative.
Okay. Negative. 3.7 to the -6 power.
Absolutely.
Yeah.
Absolutely. Okay. Rhea. Are you there, Rhea?
Yes.
Okay, Rhea. You have an H plus concentration of 5.68 times 10 to the minus fifth. I want to know what the pH is. Instructions are on the page that's exposed to you.
Okay.
What's the answer?
Do the calculations. And is it negative log?
It's negative log, yes. Okay, Rhea.
Okay.
Can you give me an answer? I don't know is a perfectly good response.
I don't know.
Ether.
It's 4.24.
Thank you, Benita. It is 4.24. Just take the number that you see there, hit the log key, type in the number you see there. You're going to get a negative number, just make it positive. Jenna, if your pH is 3.56, what is the OH concentration?
Here, let me do the calculation.
Professor, since it's the POH, are we still doing it the same way as?
Absolutely, because the POH, let me get back. The P just tells you to take the negative log. If pH is equal to negative the H plus concentration, then POH is equal to negative log the OH concentration.
Okay.
So all you're going to do is you're going to do the same thing, only instead of plugging in the H plus concentration, you're going to plug in the OH concentration. Or instead of plugging in the pH, you're going to plug in the POH.
Okay.
Was it Jenna? Who did I ask to do that? Jenna?
Me. Yeah, Jenna. I got 2.75, 10 to the -4.
Absolutely. Good. Jennifer, if your OH concentration is 9.43 times 10 to the minus ninth, what is the POH?
I'm solving it right now, so give me a second.
Okay.
So just to make sure, you would do 10 to the negative concentration of the OH, and would you get 0.99? You would round it to like 1.
1 second, okay?
Okay.
Okay, I don't understand how you got 0.99. Jennifer.
What I did was I did 10 to the power of the negative, the OH.
That's not how you do that.
You do log.
Look, the strategy. If you've got the concentration and you want the pH, you hit the log key.
would you get 8.03?
8.03, exactly. Okay. Now, a hard problem. The pOH is 10.67. What is the H plus concentration? Ethan, you think you're capable of doing this? Look at the screen, Ethan. Do you think you can do it?
Yep. Wait, okay, so.
All right, 1 second.
Oh, wait, what was.
What you're going to use is pH plus pOH is equal to 14.
Okay, so let's see. You subtract 10.67 from 14. Okay, so the pH is 3.33. And
yep, the pH is 3.33.
And then from there, you kind of plug negative 3.33. And it's like 10 power. And you get like 4.68 times 10 to the negative 1, 2, 3, 4.
Exactly. pH is 1.23. Remember, pH plus pOH is equal to 14. Jana.
Yes.
What is my pOH if my pH is equal to 1.23?
I'm sorry, you cut off. Can you repeat again?
If my pH is 1.23, what is my pOH? Remember, pH plus pOH equals 14.
12.77.
12.77. Okay, we're going to go with Emily. If my pH is 12.24, what is my pH?
1.76.
Do the last one for me, Emily. If it's 3.16, what is my pH?
Um, 10.84.
Okay, guys, you're going to need, these things are going to have to be like that. You have to realize if you have a pH, you have a way to get pOH. If you have a pOH, you have a way to get pH. And you have to be able to quickly go through changing a concentration into a pH and vice versa. You need to practice this. It needs to be quick because you can't spend that much time on this when your tests are involving other things. All right, we're going to get into measuring pH. We can do it by using indicators. If I have litmus paper, if I get a blue reaction, if I have blue litmus paper and it stays blue, or if I have red and it turns blue, what that means is that my pH is greater than 8. If I have blue paper that turns red, or if I have red paper that stays red, my pH is equal to 5. There are a whole bunch of indicators. And what you can do is you can use indicators in tandem to figure out what your pH is. Let's look at these.
Jeremiah,
If, for example,
come here.
if, for example, I have a crystal violet reaction
Come
that
here,
gives
baby.
me a blue color, And I have a methyl orange that gives me a red color.
Come here. Come here.
Ah, crap, I forgot to do something. Okay, if I have a crystal violet that is blue and I have a methyl orange that is red.
Psst, 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 psst. Come here.
Okay, who's yelling, come here?
My bad.
Please mute yourself. Thank you. If I have a crystal violet that is blue, that means that my pH has to be greater than blue or greater than 2. But if I combine that with a methyl orange that is red, that means that my methyl orange has to be less than about 3.2. So if I combine those two results, I know that my pH is somewhere between 2 and 3.2. If I have a brome phenol blue, that is blue. And I have a thymol blue that is yellow. That means that my pH of brome phenol of my solution, if it's blue and brome phenol blue, it has to be greater than about 4.7. If it's yellow, it has to be less than 8. So my pH is somewhere between 4.8 and 8. Are we kind of understanding what is going on here? Leonardo, are you there, Leonardo?
Yeah, I'm here.
I have a phenol red that is red. And I have a alizarin that is red. Tell me the range of my pH.
Probably like 8.3 to about 11.
Okay. The brome thymol blue. Did I say phenol red?
You said phenol red.
Sorry, phenol red. That is red at about 8.3. And my alizarin stays red at maybe somewhere about 11.5. So my range is 8.3 to about 11.5. Let's go. Jordan.
Yes.
I have a methyl red that is yellow. I have a alizarin yellow that is red. Methyl red is yellow. Alizarin is red. What can you say about the pH?
Methyl red looks like it's close to like 6 or 6.1. And then the other one,
It's red.
maybe like 11.2 or 3.
Okay.
So the pH is from 6.1 to 11.3.
But can it be that low? Because alizarin yellow is yellow at 10.
Oh, I'm sorry. I was looking at the one that's higher up.
You're looking at the methyl red? When
That
you're
one and then
interpreting this, if the pH is at 11, Jordan, right? What color is the methyl red going to be? The pH is 11. What color is the methyl red? Understand these colors continue on that way and they continue on that way. So if my methyl red is greater than 6.1, it's going to be yellow. If my methyl red is less than 5, it's going to be pinkish. So the question I have for you is, if it's at 11, what color is the methyl red?
Yellow.
So the methyl red really did nothing for you, did it?
No.
I said the alizarin is red. That meant that my pH has to be greater than 11. That satisfies methyl red as well as alizarin. Does that make sense, Jordan?
Yes, I was looking at the wrong alizarin, that's why.
Oh. My bad.
I'm
My
sorry.
bad. I meant alizarin yellow, and I didn't realize there was, looking at this, I didn't realize there was another one. Let's give you another one. You have bromothionyl blue that's blue, and you have a phenol red that's red. What can you say about the pH of your solution? Bromophenol blue, fourth one down is blue. My phenol red is red. What can you say about the pH?
The blue is like maybe like 4.8.
4.8 up to 14, right?
Yes,
What about my phenol red being red?
like 8.2.
So can it be anywhere from 4.8 to 8.2? Can it be that pH?
Yes.
It can't, because if it was less than the 8, the phenol red would be yellow.
So it has to be greater.
It has to be greater than, it has to turn the phenol red red. So it has to be a pH that is greater than when it's yellow. So somewhere maybe, in this, maybe about 7.5.
Okay.
If my pH is 7.5 to satisfy the fact that phenol red is red, isn't my bromophenol blue also blue at 7.5 pH?
Yes.
Let's get another one. Parker.
Yes.
Parker,
Yeah, I'm here.
I have a cresol red that's red. I have a phenol red that's yellow. What can you say about my pH?
So you said a phenol red that's yellow, and what was the first one?
Phenol red that's yellow and a cresol red that is red.
So it's got to be below. It's gonna be like 1 or less.
Or you can say like 1.5, because it's kind of starting to turn red there. But yeah, and effectively, Parker, yes, you're absolutely correct. Ethan, you have a crystal violet that's blue, and you have a brome cresol green that is yellow.
Okay, crystal violet, that's
That is
blue and
blue
what?
and a brome cresol green that is yellow.
Well, it's gonna be between like 2 and 4, so I guess like 3.
No, don't say.
Well,
say the
I mean,
range.
but I guess between 2 and 4 as the.
Between 2 and 4. You
Yeah.
have to give me a range there, Ethan. Okay? Does that make
Yep.
sense?
Mm-hmm.
Okay. We also can use something called a pH meter. And basically, all a pH meter does is it measures the voltage that a solution has. The more ions, i.e. the more H3O, the more voltage it's going to have, and it's going to change that voltage into an LED readout. All right, remember, Ka's are the same as equilibrium constants. If I give you the pH, you can get the H3O concentration. Is that correct, ladies and gentlemen? If I give you a pH, you can determine what the concentration is, correct?
Yes.
Correct.
Yes.
So I can use those concentrations to determine what my Ka is. I've got a 0.10 molar solution of formic acid. The pH is 2.38. Can I get the H3O concentration? If I have a pH, can I get the H3O concentration?
Yes.
Thank you. Thank you very much, Natalia. So I'm going to use the pH to get my H3O concentration. I have one more bit of information. I got a couple of bits of information. I guess I didn't put it in there. Okay. I also know in this particular instance, I also know what my reaction is. I've got HCOOH plus H2O making HCOO minus plus H3O. Can you tell me what the relationship between my HCOO minus is and my H3O plus? Come on, guys, it's stoichiometry. What's the relationship between H3O plus and HCOO minus?
1 to 1.
So if I know the concentration of my H3O plus and it all came from HCOOH, do I not also know my formate concentration?
Yes.
Okay, so we also know our equilibrium expression. We're going to take our concentration of H3O, our concentration of formate, and divide it by the concentration of my formic acid. We also have that bit of information. We can find the H3O, which is the same as the formate, from the pH. Again, I am going to take the pH. I'm going to hit the 10 to the X key, type in negative 2.38. That gives me the concentration of my H3O, which is the same as my formate. Now I'm going to simply use an ice table. Initially, my formic acid was 0.10 molar. I had no H3O, I had no formate. At equilibrium, I know the concentration of my H3O because I figured it out from the pH. The concentration of my formate is the same as my H3O. So the change of both of those is a plus 4.2, 10 to the minus 3. Stoichiometry between H3O plus and formic acid is 1 to 1. So if I gained that much hydronium ion, I lost that much formate. So I'm going to take my 0.1 minus 4.2 times 10 to the third. This gives me about a 0.10 solution, accounting for significant figures. All I do now is plug all the values in to my Ka, and I end up with a Ka of about 1.8 times 10 to the minus fourth. Guys, you're going to get sick of ice diagrams. All right. This is going to be an ice diagram. We have nitrous acid. We start off with 0.500 molar nitrous acid. I'm also given the Ka. I have my reaction, which is HNO2 plus water makes H3O plus plus NO2 minus. Do I know what the concentration of my H3O or NO2 at equilibrium are? Natalia, do I know what those concentrations are? Does the problem give me the H3O concentration or the NO2 minus concentration?
No.
No. So I'm going to call it X. If my H3O concentration is X, so is my NO2 concentration. If I started out with 0, that meant that I added a positive X H3O, I added a positive X NO2. I have a negative X for the NO2 because these two came from it and it's a 1-to-1 relationship. So at equilibrium, I have 0.500 molar minus X of my nitrous acid. I have X of my H3O and X of my NO2. Is this a small number compared to 0.5? Is it a small number in comparison
Yeah.
with 0.5? Thank you. So what am I going to do about this X here?
Does it become 0?
We're going to assume it's 0. I'm going to put in my 4.6 times 10 to the minus 4. I'm going to add my concentration of H3O. I'm sorry, erase what I just said. My Ka is equal to 4.6 times 10 to the minus 4th. X times X, my concentration at equilibrium of H3O plus and NO2 minus is going to be X squared divided by my HNO2, which is 0.500 minus X. We're going to assume the X is 0. It's negative. I simply multiply my Ka by 0.5, take the square root of it. That is what my X is. Tell me what X is. I've solved for X. What is X? Benita, what is X?
The concentration of H3O plus.
Okay. Now, Benita, if I have the concentration of H3O, can I get the pH?
Yes.
So I'm done with my equation. My answer was 0.015 is equal to X. I first check to see whether I can use it. 0.015 divided by 5 is 3%. So yes, I can use the assumption that X goes to 0. My pH is negative log of my concentration. You said, Benita, that my concentration was 0.015 molar. The log of 0.15 molar is a negative 182. I make that number positive. My pH is going to be 1.82. Questions, ladies and gentlemen? Now, there is another term called percent ionization. It's a simple term. All you're going to do is take the concentration of your H3O plus and divide it by the initial concentration of your acid. In this particular instance, my H3O concentration, let's use the real example. Here's the example I just did. If I divide 0.015 divided by 0.1 multiplied by 100, I get 15%. So when I'm doing percent ionization, all I'm doing is finding my concentration of my H3O. I'm going to take that and I'm going to divide that by my initial concentration of my acid. And this is going to tell me how much of my acid by a percent basis was ionized. Questions, ladies and gentlemen? We're going to be doing another 70 pages of ice diagrams, guys. Oh boy, I'm sure you're saying. Okay, 1 second, guys. Let me see where I was. Calculate the pH of a 0.30 solution of acetic acid at 25C. Ka for acetic acid is 1.8 times 10 to the minus fifth. Manual? You there, Manual?
Yes.
Okay, what is my, I gotta see where I'm at. That's right, okay. Manual, what is my equilibrium concentration? Or what is my Ka expression?
Is it 1.8 times 10 to the negative 5?
That's what it is. What's the expression? What are the concentration terms?
I'm not sure. I'll be honest.
Okay.
Positive.
All right, Manuel, can I ask you a question? If this was an equilibrium, and it is, can you tell me what Kc would be?
Kc would be products over reactants. So H3O plus times C2H3O2 over HC2H3O2.
That's what I'm talking. When I say what is the equilibrium expression, that's what I'm asking for. Okay, Manuel?
Oh, gotcha.
So I've got my equilibrium expression, which is this. Now we're going to put the ice diagram. Manuel, what do I have originally?
You have 0.30 molar of acetic acid.
Do I have any H3O or acetate?
You do not.
So I have none of that. I got 0.30, 0.03, and 0 and 0. Okay. At equilibrium, do we know how much H3O we have? Or do we know how much C2H3O2 we have, Manuel?
We don't.
So what are we going to call it?
X.
If H3O is X, what's the value of C2H3O2?
Also X.
So I'm going to plug that in. I'm going to have X here, X here. That means that I've gained positive X of H3O. I've gained positive X acetate. I've lost X of my acetic acid. So at equilibrium, I got 0.30 minus X. Now, my Ka value was a very small number. Can I assume that X is equal to 0? When I'm subtracting it from the 0.30, Manuel?
Are you talking about the X is small approximation?
Yes, I am.
Yep. Yeah, it's a small number, so it wouldn't affect the accuracy of.
So my Ka is going to be equal to X squared divided by, this is my acid concentration. Normally it would be 0.30 minus X. I've assumed X is 0. I solve this out for X. I get a value of 2.3 times 10 to the minus third. Now, what do I do?
Well, since that's your concentration for X, you plug in to the ice table to see the difference of changing.
What's the question asking me for, Manuel?
I'm not sure. What were you asking me?
There's a
Oh,
question.
for calculating the pH. So we take the negative log of the H protons, so it'd be negative log of 2.3
Times 10 to the minus third.
3, yeah, and then that would give us 2.63. That's for the pH.
Okay. That's validating the 5% rule. Guys, if you use that, you have to validate the 5% rule. So as you said, Manuel, my pH is 2.64. These are the same thing as the equilibrium, only we're involving the pH in order to get concentrations, or we're involving the pH in order to get the concentration. I'm going to skip ahead. This is the same type of problem as we're dealing with, I think. Wait, maybe not. This one, I know what the pH is, so I can figure out that X is both of them. And I know that this is going to be okay. If I have this problem, I know what the pH is. Can I get the H3O concentration? Rhea,
Yes.
if I have the pH, can I get the H3O concentration?
Yes.
How am I going to do that?
By using the ice tables.
No. I know what the pH is. I know what the pH is. I need to determine what my concentration is. Do you remember how to do that?
You use the 10 to the power.
Very good, very good. But it's 10 to the negative power. So I'm going to take 10 raised to the minus 3.26 power. And that's going to give me a concentration of 5.50 e to the minus fourth. Now I'm going to set up my ice table. I know I started off with 0 H3O and 0 niacin. My niacin started off at 0.20. So I have the amount of H3O I made. I got that from determining it from the pH. I have the amount of niacin, which is equal to the amount of H3O. I had to change it by getting a positive number of that. So whatever I have of change of the niacin and the H3O, that makes my niacin negative that amount. So I have my equilibrium as being my equilibrium value of niacin, neutral niacin is 0.20 minus 5.5 e to the negative 4. I plug those values in, solve for Ka, I get 1.5 e to the minus 6. Guys, I have some more problems here that I want you to go through. Okay. I have two acids that are mixed. I have two acids that are mixed. This was a question in the, no, it wasn't. The quiz was the second proton. I have two acids that are mixed. But I have three sources of H, of H3O. The H3O can come from the HCN, it can come from the H2O, or it can come from the HF. The ratio of the Kas between these two and these two is astronomical. Now, HF is producing H3O. What did we learn about Le Chatelier? If I've got H3O present, which way is it going to shift the equilibrium of HCN plus water making H3O plus CN minus? If I already have a bunch of H3O in there, which way is it going to shift the equilibrium? To the reactants or to the products?
Would it be to the reactants? Because now you have more products.
So that means even more that the HCN is not going to generate H3O plus. That means even more that the H2O is not going to generate H3O plus. The amount of H3O produced by HCN and H2O are insignificant when compared to the HF. If they are insignificant, ignore them. The only significant production of H3O plus comes from the HF. Forget about the others. I know I have that much HF, becomes a simple ice diagram. I produce XH2O, 3O, XF minus. That I lose X from my HF. I set up my Ka. My X ends up being 2.9 times 10 to the minus 2. So if you are given a problem with different acids, look at their Kas. If their Kas are more than 3 units away from one another, ignore them. All you have to do is solve for the strongest acid. That will tell you how much H3O you're producing. Anybody have a problem with that? Parker, you good? You good with that, Parker?
Yep, I'm good with it.
Difficult problem. I have the pH. I want to know what the pH of a 2.4 methylamine solution is with a Ka of 2.27 times 10 to the minus 11. Methylamine is a base. So if I have a base, I am taking a base gets a proton from the contributing acid. So if methylamine is a base, what it is going to do is it's going to suck up an H from the H2O to make this thing, plus it's going to generate OH minus. Kas. Kas make acid. I have to have an H3O term. Do I have any acid in this equation? Is there any acid there? Parker?
Would you be able to,
Do you see
would
any
you-
H3O? Kas need an H3O. Is there an H3O generated in this equation?
no,
So I can't use a Ka. However, a Kb is going to employ the concentration of OH minus. So if I have a way of turning my Ka into a Kb, I can solve this problem. Make sense, Parker?
yes,
I have that. I know that Ka times Kb is equal to Kw. There are two formulas that you need to put prominent to have access to them. pH plus POH is equal to 14, or Ka times Kb equals Kw. I have my Ka. I multiply that by Kb. This is going to equal Kw, which is 1 times 10 to the minus 14th. I do that value out. I get a value of 4.40 times 10 to the minus 4th. That is the trick you need to use if you are given a Ka in a basic equation, or you're given Kb in an acidic equation. After this, all I got to do is set up the ice table, solve for OH minus. Then I'm going to change the OH minus into POH, and I'm going to use the formula pH plus POH equals 14. Ice table. Parker, can you do this real quick for me?
sure. Just hold on, give me a second. I'm gonna write it down. Okay.
What's my initial concentration?
So the initial concentration is 2.4 for the first one, and then 0 and 0.
Okay. What are my concentrations? Let's see. Let me get back to that. So I'm trying to find where the original equation is.
I think it was right before that. One more.
There we go. All right, that's the original equation.
Yeah, so we only have the CH3 and H2 given.
Okay, that's the equation. All right. And we said the ice, you wanted to put this as what, 2.4?
Yes.
0 and 0. What's the equilibrium?
It's going to be 2.4 minus X, and then it's just going to be X and X.
Basically, I knew I produced X amount of this and X amount of this. That gives me a plus X here and a plus X here. That means that I got a minus X there. That's how I generated my three numbers. My KB solution is X squared over 2.4 minus X. We're going to disregard the X. I solved for my X concentration, which is 0.0032. It satisfies the 5% rule. Now, you got to ask yourself, what is X equal to? Parker, what's it equal to?
The concentration for OH,
What am I asking?
for pH.
So I have to change my concentration of OH into a POH. Then whatever my POH is, I have to subtract it from 14. I get a POH. If I do that math out of 3.49, 3.49 plus pH is equal to 14. So if I subtract the 3.49 from 14, I get a pH of 10.51. Questions, ladies and gentlemen? The trick there, if you're given a Ka and it's a basic reaction, you have to change the Ka to a Kb. Then you have to realize, once you have solved for X, you have to realize that X is not H3O, X is actually OH minus. So you then have to convert it to a POH and subtract it from 14 to get the pH. Is there another way I can solve for the pH here? Remember, my concentration of OH times the concentration of H plus equals 10 to the minus 14th. If I have my concentration of OH, I can solve for my H plus concentration that way. There are more than one way to solve these problems, guys. I got 4 minutes left and I don't really want to get into, yeah, I'm going to get into it and then I'm going to start this off on Tuesday. Okay, if I have a reaction of an acidic proton like NH4, my NH4 can react with water to donate a proton from that NH4 to the water, making H3O. If I have a metal cation, that metal cation can grab the OH away from H2O, making H3O. I've got an H plus water, that would make H3O. So if I have a cation, or if I have an NH4, each one of those will generate an H plus. The NH4 from donating the proton directly, the cation from grabbing the OH from the water and making the metal OH, metal hydroxide. But what that leaves is H plus, which reacts with water to make H3O. Okay. So we got to think about what we're doing when we're making conjugates. Remember, I said strong acid, weak conjugate base. Weak acid makes a strong conjugate base. Strong base, weak conjugate acid. Weak acid, strong conjugate base. So if I have a strong conjugate base, that strong conjugate base is going to grab a hydrogen from water to regenerate the weak acid. But looky, I'm making OH minus. So if I just had A minus, what would my pH be? Would it be bigger than 7 or less than 7? What am I generating, guys? What am I generating?
Hydroxide ions.
I'm generating hydroxide ions. Hydroxide ions have a pH greater than 7 or less than 7.
Greater than 7.
So I'm effectively taking an anion, reacting it with water, and I'm making base. Similarly, if I take a cation, an M+, react that with water. If my conjugate acid is strong, I react that with water, it pulls an OH away from it, making MOH, plus I generate H+. So if I have a strong conjugate acid, I'm generating H+. Which way does the pH go? I'm generating H+, guys. Is that an acid or a base?
Acid.
So what's my pH going to be, Jenna?
Less than 7.
Less than 7. Now, if I have a weak conjugate base, I don't get any reaction. If I have a weak conjugate acid, I get no reaction. So for the weak conjugate base, I do not make H+. For my weak conjugate acid, I don't make OH-. If I pair a strong conjugate base with a weak conjugate acid, what happens? In other words, if I have a salt, Pa, put that in water, this dissociates to P+ and A-. My P+ plus water, I get no reaction. But my A- with water generates a weak acid plus OH-. What is the effect on the pH? What am I generating? You're muted, Jenna.
Hydroxide.
So what
Ion.
is my pH going to be?
Greater than 7.
So all I'm doing is I'm taking a salt. You normally think of salts as being neutral, but I'm putting it into water. If my P is a weak conjugate acid and my A- is a strong conjugate base, overall, I'm generating OH-. My salt is making a basic solution. If I do the opposite and I have a strong conjugate acid and a weak conjugate base, I generate H+. So if I have MW, my M reacts with water to make H+, my W- doesn't react. My pH decreases. Okay, I went 3 minutes over. I apologize for that, ladies and gentlemen. Work on pHs and converting them back to POHs. Work on the ice diagrams. The extra homework will help, guys. You also need to realize that if I have two acids, the strongest acid is going to be the only one that's really going to generate the H3O. If I give you a Kb and it's an acidic reaction, I have to change the Kb into a Ka by multiplying it. Kb times Ka is equal to Kw. That will give you the Ka, then do the ice diagram. We're going to get more into this type of thing on Tuesday, and then we're going to get into buffers. Questions, ladies and gentlemen? Okay, I got to get out of here. So I will see you again on Tuesday.
Bye, thank you.
All right, bye. Araceli, Natalie, Ria, Cherie. Ria, Cherie. Are you still there? Cherie, are you still there? Cherie, please log out. Cherie. Cherie? Okay, Cherie. I am going to give you only half credit for today's appearance because you left early. Araceli, what do you need?
Oh, sorry. I heard my name, but I accidentally clicked on the leave button, but I heard my name. So I was like,
No. I didn't
Oh.
call. What I was calling you for was to log out if you have no questions.
oh, okay.
All right.
Oh, bye-bye. Thank you.
Bye. Take care.
You too.